In this lesson, we're going to learn about complex numbers and imaginary numbers, see what they are, and see how we can work with different expressions that do have imaginary numbers in them. And so first, what the heck are imaginary numbers? What am I talking about? So I'm going to answer your question with the question, what are the solutions to this quadratic function? Okay, so we know that solutions happen when we cross the x-axis, and so what would the solutions of a quadratic like this be? And you may think that, well, it never crosses the x-axis, so there's no solutions. And that's where you're wrong. That's where these mathematicians came up with a fun little game called imaginary numbers, where we can find solutions to quadratics like this that don't touch the x-axis. Okay? And so imaginary numbers, an imaginary number is the square root of a negative number, right? So if we think about doing 2 squared, 2 squared would be 4, but also if we had negative 2 squared, so we can say 2 squared is equal to 4, but negative 2 squared is also negative 2 times negative 2 also gets you positive 4. So it's impossible to square a number and end up with a negative number. And so that's how we get the imaginary unit, which we call I. And so I'm going to try and write this out here. I, and I'm going to use this like cursive I, is the imaginary unit, which is the square root of negative 1. Okay? Now a complex number is just a real number and an imaginary number being combined. And so usually we write this as a plus bi, where a is our real number. And since b has the I with it, this is going to be our imaginary number. Okay? That also leads us to what we have, what we call a theorem. It's something that's always true in math. So if we know that the square, or that, I is the square root of negative 1, then I squared, okay, so if we're squaring something, this is going to be negative 1, okay, because if I took this and I squared it and I squared this, the square root and the square would cancel, which means I squared would just be equal to what's left inside the root, which is negative 1. So I squared is equal to negative 1, and I is equal to the square root of negative 1. Okay, so that's going to be important in a couple of examples here, but let's do these two first. So first, just simplifying a square root with a negative. First thing I can do is, since I have this negative, I'm just going to move that out as I, okay? Anytime that we have a negative inside the square root, it's going to be imaginary, so we can just take out the I before we get started. And now we can try and find numbers that multiply to 72. Well, I can say 2 times 36 multiplies to 72, and 36 is actually a perfect square. It's 6 times 6. So I've got a pair of numbers here. So I'm going to pull that outside of my square root. And I'm going to bring down the I that we wrote at the beginning. And now the only thing left inside my radical would be this 2. So I take this 2 and bring it on the inside. So the square root of negative 72 can be simplified to 6i square roots of 2. We can also add and subtract different complex numbers, right? So this is a complex number and this is a complex number, just like we did, where we have our real and imaginary unit. And whenever we're working with these i's, these imaginary numbers, we can treat it just like an x, just like a regular variable. So what I'm going to do is I'm going to distribute this negative because it's going to change the signs of both of those terms in my second complex number. So I've got 17 minus 6i minus 9 minus 10i. Again, I'm just changing those signs. Now let's find our like terms. Well, I've got this 17 minus 9. That's going to give me 8. And then negative 6i minus 10i leaves me with negative 16i. Okay, 2 more examples here. Now let's multiply. We're going to multiply some complex numbers now. And again, we can use the FOIL method or we can use the box method. I usually prefer doing the box, just helps me keep my numbers a little more in order. So I'm going to take my first complex numbers, so 4 plus I on top, and 7 minus 3I down the side. So 7 times 4 will give me 28. And now I times 7, again, we're just treating I like a regular variable. So I'm going to say this is plus 7I, just like I would say plus 7x. 4 times negative 3I. 4 times negative 3 would give me negative 12. And then I'm just going to throw that I on at the end. And then I times negative 3I would give me negative 3I squared. Okay, and I see I have this squared now, and if we think back to the original theorem that we wrote, let's remember we said I squared is equal to negative 1. So here, when I have this I squared, I can cancel that out and say that's negative 1. So now I have 3 times negative 1, which is actually just going to give me positive 3. And now we can combine our diagonals here since both of those are like terms. So 28 plus 3 would give me, negative 31. And then negative 12i plus 7i would give me a negative 5i. So again, i's are exactly the same as any other variable until you get I squared. Then we change it to a negative 1. And I multiplied this negative 3 times negative 1 to get a positive 3. And my last one here, I've got the square root of 4 plus the square root of negative 96 all over 10. And this is kind of going to be where these complex numbers will lead to. So first, I know that the square root of 4, that's just 2. Okay, so I'm going to write that. Plus, let's break up this 96. Okay, so I'm thinking of numbers that multiply to 96. Well, I know 96 is even, so I can say 2 times 48 would get me 96. 96. Okay, 48 is also even, so I'm going to break that up into 2 times 24. 24 is still even, so I'm going to break that into 2 times 12. 12 can be broken into 3 times 4. And 4 can be broken into 2 times 2. And I'm going to cross out everything that I broke up further so I can kind of see stuff a little easier here. Now let's find some pairs. I see I have a pair of 2's here and a pair of 2's here. I cannot do anything with this 2 because I don't have another 2 that's going with it. So I'm going to say 2 times 2 when I pull that out. I'm also going to have an I because it's negative. And then inside the radical, I'm left with 2 times 3. And all of this is being divided by 10. Now let's clean this up a little bit. So again, I pulled out one pair of 2's and another pair of 2's, and those come out as single. But I can multiply those now. I'm going to have 2 plus 2 times 2 would give me 4i. And then inside the radical, 2 times 3 would give me 6, and all of this is divided by 10. Now I'm going to look at my 3 numbers. I've got a 2, a 4, and a 10. I can divide all of those by 2, so I'm going to do that. When I do that, 2 divided by 2 is 1, plus 4i divided by 2 would give me 2i. I cannot do anything with whatever is inside the radical, so I'm going to keep that the way it is. And then 10 divided by 2 is 5. So again, this is a much more complicated example than the other ones, but this is eventually where we're going to get to when we're working with complex numbers. Okay, so what are complex numbers? What are imaginary numbers, and how do we work with them? Imaginary numbers is just the square root of a negative number. Okay, we know that getting a square root of a negative number is impossible. And so we've invented what we call imaginary numbers to work with those. Complex numbers are real and imaginary numbers being combined. And we work with them just like we would work with any other variable, okay? We can just say that it's an x and combine it until we get I squared, which we know is -1. And then we can adjust our solution to be with that. So I hope you had as much fun with I did learning about imaginary numbers. Good luck in your practice, and I'll see you in the next video.